All right, can you see my screen?
Yes, sir.
Okay, great. So far we have been trying to understand convex functions from all different angles. That we defined it a certain way, and then we showed like that a function is convex if and only if its epigraph is convex. And then we studied like Jensen's inequality and how to build new convex functions from old. So all our focus in this part, after let's say like simplex algorithm and duality, after all those concepts in linear programming, our focus has been about understanding convex functions and looking at various examples. So in the previous lecture, a big part of it was proving that every convex function, for example, is can be expressed as the supremum of a family of affine functions. So that was the big result we proved in previous class. And we also have a recipe for building new convex from old convex functions. And one of the last things I did was talking about minimization of a family of convex function. So I think that was not very clear to some of you. So maybe I'll just repeat that. So this is also another recipe of building a new convex functions from old functions. And one of the assignment exercises is also of a similar nature, where you start with a convex function, and I guess I can right away give you the solution to that question. In a sense that all you have to do to conclude that this quadratic function is convex is just compute the Hessian. It's a nice smooth function. So compute the Hessian and check whether it is positive definite or not. So that would imply that the function is convex. I mean, positive semi-definiteness is enough to conclude it's convex. But if you want something like strictly convex, then you need positive definiteness. Okay. So let's go back to that example very briefly. So minimization. So what we have already seen is supremum of a family of convex functions is convex. Here, let's say you have omega is a convex domain in Rn cross Rm. So this is a convex domain, meaning it's a convex set and it has non-empty interior. That's what domain means. It's non-empty interior. And let's say f is a function from Rn cross Rm. Oh, sorry. I want it to be on omega actually. So from omega to R is convex. So starting with this function, we can actually build new convex functions by some sort of projecting down. So if you define g of x in this manner, so infimum of y in C, f of xy, and here C is some non-empty convex set in Rm. So here C is some non-empty convex set in Rm. So typically, like the domain of G here, first of all, will consist of all those x's in Rn such that there is some y such that xy belongs to domain of f, which is actually omega. So otherwise, like you don't consider such x. In fact, f of xy will not even be defined. If there is no y, then this set over which you're taking this infimum is empty. There's nothing to do here. So that is not included in the domain of G. But what could possibly happen is g of x is actually minus infinity, right? This infimum could be minus infinity. So this is also again one of the assignment exercises to show that if for some point g of x is strictly bigger than minus infinity, so if g of x is bigger than minus infinity for some x in domain of G, I can give you a hint as to how to proceed. The conclusion is that g of x is bigger than minus infinity for all x in domain of G. So here you can use some sort of compactness argument. Like whatever set you take, you can write as a union of compact sets. So you can take like compact balls and make them bigger and bigger. And here you have to note, again, another of the assignments is about proving that every convex function is continuous in the interior of its domain. On the boundary, it may not be continuous. So there you have to give a counter example. But in the interior, it is always going to be continuous. So if g of x is bigger than minus infinity at some point, then there is a neighborhood where it is bigger than minus infinity. and then you keep and if you have a compact domain, for example, you can try to slowly cover it up with all these open sets, and eventually you'll have some sort of finite covering, and each of them is bounded below, so you can take the mean of that. So that is the strategy you can use to show that if g of x is bigger than minus infinity for some x, and knowing that g is continuous, we can actually show that it's going to be bigger than minus infinity for all x in the domain of g. All right, so knowing this, so all we need is to say either it is identically minus infinity, which is not very interesting, or if it is not minus infinity, it is never touches minus infinity. So in that case, so our claim was that if g is not identically minus infinity, then if g is not identically minus infinity, then g is convex. So essentially, we built up a new convex function from this old convex function, which was defined on a higher dimensions. We essentially sliced it up. So if you are talking in 2 dimensions, for example, and the third dimension represents the value z equals f of xy. And so let's say we have this convex set. So this is my x-axis, this is my y-axis, and I have some sort of paraboloid kind of thing here. So what this is claiming is if I'm fixing x, so I'm fixing this value of x, then in the domain, it consists of these points, right? And for each of them, I will take an infimum. So infimum over y. So perhaps it happens somewhere here. And at this point, the infimum may happen over here at this slice. So you're slicing your convex domain. And as you can guess, all the slices will themselves be convex. And again, another assignment exercises asks you to prove that if something is a local minimum, it is a global minimum. So that and pictorially it is clear, convex functions somewhat look like this. And here also I can give you a hint as to the answer. Essentially, it goes back to the supporting hyperplane theorem, the separation theorem, and so on. The supporting hyperplane theorem is a local thing. If I isolate, I take a ball around this and take intersection of this convex set here, and I have a supporting hyperplane, then it will also be supporting for the whole convex set. That's the way convex sets are designed. Like if you have a local supporting hyperplane, it's a global supporting hyperplane. And if you have a local minimum, this is a local supporting hyperplane, and hence it's a global supporting hyperplane, which is parallel to this domain kind of thing. Then that will serve as the global minimum. So I already gave you the proof, but you have to write down the correct words. All right. So here the claim is, so for each x, I have this smallest value. And the claim is that this new g as a function of this interval. Now this g is a function of this interval. And the claim is g is convex. And the way we showed is essentially we have x1, x2 in domain of g, which means there exists y1, y2 in Rm such that x1, y1 and x2, y2 first of all belong to omega, which is domain of f. Otherwise, like f of x comma y is not even defined. There is like nothing in that domain. So for example, at this point, this convex set has like no points lying there. So talking about infimum doesn't make any sense. So now that we have this y1 and y2, and because f is equal to, because g is the infimum, that means if I increase this value g of x by epsilon, then that value is actually attained for some y. Infimum may not be attained. For example, if I have a sequence 1 over n, the infimum is 0, but 0 is nowhere in that sequence. But if I perturb it by a little bit, if I add epsilon, maybe I add like 1 over 100, then there is some point in that interval 0 to 1 over 100 which lies in that sequence. So here I will choose such an epsilon. So there exists y1, y2 in the domain such that f of xi, yi is less than equal to g of xi plus epsilon. So here I is just 1, 2. I'm just talking about these 2 points, x1, x2. And here, since g is that infimum, if I add epsilon, then there is something in that set over which you're taking infimum, which is lower than this gx plus epsilon. And here, by the way, epsilon is strictly bigger than 0. And here we are able to use convexity of f to give some sort of inequality, like to show Jensen's inequality. So g of theta x1 plus 1 minus theta x2 is less than equal to infimum of y over y yeah so such that this quantity theta x1 plus 1 minus theta x2 y actually belongs to the domain of f, and we know that this is not empty because x1 y1 is in the domain, x2 y2 is in the domain. So if I do theta x1 plus 1 minus theta x2 and theta y1 plus 1 minus theta y2, so there is at least one such y for which f is defined, but we are taking infimum over many such. But since this is the infimum, what we do know is for any particular choice it is going to dominate this value. So this is less than equal to f of theta x1 plus 1 minus theta y2 x2, and here I will take theta y1 plus 1 minus theta y2, and here I will use Jensen's inequality for f. F was given to be convex. That's the old function, old convex function we started off with. So this is less than equal to f of x1 y1 plus 1 minus theta f of x2 y2. But this we know to be less than equal to gx1 plus epsilon. This is gx2 plus epsilon. So this is less than equal to theta gx1 plus 1 minus theta gx2. Then you have a theta epsilon and a 1 minus theta epsilon, which I'm going to collect as an epsilon here. So here what we have shown actually in this inequality, so for given x1, x2 in the domain, this inequality always holds no matter what epsilon is. So given epsilon, the yi's will depend on epsilon, but in this final inequality, that dependence has gone away. So this is true for all epsilon bigger than 0. And this implies as long as x1 and x2 are in the domain of G, this inequality holds. So which shows that G is convex. So this is another way of building a convex function. If you already have a convex function in a higher dimension, essentially you're taking certain slices. And it's not like I'm saying that I'm taking a restriction to some sort of this line. That would be convex in a very trivial fashion. If you restrict to certain lines, those will be convex. We have already seen that convex is actually somewhat of a one-dimensional concept, although we have defined it in general for higher dimensions. But the true essence of convexity lies in one dimension. It's talking about line segments, right? Give me 2 points in the epigraph, the line segment joining them belongs there. So that's why we had all this theorem saying that if directional derivatives exist, then the total derivative also exists, which we know from analysis 3 not to be true in general. And in fact, more is true as long as the partial derivatives with respect to the coordinate axis exist, then the total derivative also exists. So convexity is a very kind of a strong assumption. But this is not what's going on here. We're not taking like straight slices. At each line, we're taking some infimum. It will be somewhat of a continuous thing, but it is varying. But still, as parameterized by x, whatever infimum we get is going to be a convex function. That's what's proved here. So in fact, we're getting something new rather than just deleting some coordinates or doing some affine transformation and so on. All right. So I hope this was clear. Or if there are any more questions, please feel free to ask. All right, so I'm going to assume this was clear. And the next notion we are going to talk about is the notion of duality for convex functions. So these are also known as conjugate functions. Already in the context of linear programming, we have seen the notion of duality. First of all, for a linear program, we had this dual linear program, but we saw that eventually it turned out to be a geometric concept. It was about polar bodies and so on. So it is very natural to expect that there is also a notion of duality for convex functions, because there is a very nice convex set attached to convex functions. That's the epigraph of f. And we'll give an interpretation, just like we had an economic interpretation of the dual. Remember, like when we were doing linear programming, like the optimization problem for the primal variables, we had this cost function which was c1 x1 and cn xn. Perhaps maybe let me add a start to show that this is the optimal solution. And what this was telling us is if I increase the cost function by amount of c1, then like by 1 unit, then the total profit will increase by x1 star unit. So like, how should I optimally vary the profit? And the dual thing was, if I change the resources, so if I have B1 U1 star up to B M U M star, the interpretation of the optimal dual variable was essentially, if I increase the resource one by 1 unit, how much will the profit increase? So that was the duality. So similarly, we will have an economic interpretation of the duality for convex functions. But before that, let me first even define what a dual of a convex function will be. So let's say this is a convex function defined over all of Rn, but you can also try to restrict to omega. Now, given a vector in Rn, f star of u is equal to supremum of x belonging to domain of f, let's say omega, of this quantity, u dot x minus f of x. All right. So, and u is some vector in, is going to be some vector in Rn. So this is known, so f star is known as the conjugate of f. Okay. Yeah, so and domain of f star is wherever supremum exists. Otherwise, if it is plus infinity, I'm just going to delete it from my domain. So sometimes what people do is, to make this theory cleaner, they will just say convex functions are those functions which take values in R union plus infinity. So that all these statements, like the domain is always Rn. If it is defined on omega, outside of omega, I'll just define it as plus infinity. So the epigraph is always going to be like convex in the sense that you have the graph here, and rest away it is just plus infinity. So in that case, you don't have to worry about what the domain is. And for example, here, instead of saying domain of f star is wherever supremum exists, I could have just written domain is all of Rn, but wherever supremum does not exist, you're defining it to be infinity. So all these are just some sort of notational jugglery. It just makes your life simpler not to have to talk about cases, different types of cases. Does the supremum exist? Does it not? And so on. But any case, so those type of things actually make statements of theorems actually much cleaner, since you don't have to consider various cases. But here, since we're talking about applications and so on, let's stick to finite things. All right. So how do we interpret this? So let's rewrite this function, this conjugate function of a convex function. So that is the smallest real number such that the epigraph of f is contained in hu minus 1, the closed half space governed by alpha. So if I have this convex function and I chose this vector u, so here remember R, like my domain is R. So u is in fact, again, f star is going to be a function on R because f is a function on R. So u minus 1, so I'm fixing this number minus 1. So these are the like vectors you're really considering in u minus 1. And the normal to this, for example, this vector. So for example, to this vector will look something like this. And remember, alpha is always the offset. So if this is the epigraph of f, so by how much should I offset? So like, what is the smallest? If I go all the way here, of course, that offset will also contain the epigraph. It's just talking about the smallest thing, smallest supporting hyperplane. So essentially, it is providing a parametrization of the setup supporting half spaces of the epigraph. Provides a parametrization of the set of supporting half spaces of the epigraph of f. So this is essentially something like that polar body we had talked about, or the support function, things like that. All right, so then you might be wondering, where did this minus 1 come from? So here actually we are dealing with convex. So this convex body is not in Rn, right? It is in Rn plus 1. So one of these coordinates is supposed to represent value of the function. Rest of them are the dependent variables. So here, when I'm talking about duality, first of all, I cannot, like, there are some distinguished lines. For example, vertical lines are not allowed. For example, this quantity cannot be 0, equal to 0. That would mean that your line is actually vertical, your half space is vertical. Those we don't really consider as supporting half spaces, although for convex bodies generally we would. But here for convex functions, we want to avoid these vertical lines. So first of all, this need not be positive. It need not, has to be non-zero. But if it is negative, you will have supporting half spaces. For example, if it is positive, then essentially it will be like a reparameterization of whole thing. So as a normalization, you first of all you have to assume that this quantity can never be zero, and then you normalize it to -1, and correspondingly alpha will reflect that normalization. All right. So again, coming back, so given a convex function, the conjugate function effectively gives you a parameterization of the set of supporting half spaces of the epigraph of f. Okay. So now f star again is actually a convex function. So why so? So let's stare at the definition. Can someone quickly tell me from the definition why f star should be convex? So look at this function. For a given x, what kind of function is this? It's an affine function, right? X is fixed, u so supreme, okay, sorry, x is not fixed, u is fixed. So now this is a function of x, and it's an affine function. No, I think no, this won't be an affine function because f varies. So we have to keep x fixed. Right.
Minus of this is convex, so the infimum will be convex.
No, in fact, it's an affine function. So it is both convex and concave. So what you said is correct. Minus of this is convex, but this itself is also convex. And here, essentially, think of this as a function of u. So g of u. So x is fixed. So this is a function, affine function of u. So here, hence it is convex. It is both concave and convex. Now we're taking supremum of convex functions. So hence f star is also convex. So from what we have seen before, that supremum of convex functions, arbitrary supremum of convex functions is convex. So hence this conjugate function is also convex. Okay, and we can rewrite it another way. So f star u is the minimal offset value of beta such that this affine space u dot x minus beta underestimates f everywhere. This is just a rehash of what we just saw geometrically here. Underestimates just mean that it's below that function. Yeah. Underestimates f everywhere. All right, now let's look at some examples. Before going to that economic interpretation of this conjugate function, let's look at some examples. So conjugates of convex functions on R. All right, first, as usual, affine functions. So what are the conjugates of affine functions? These are the simplest convex functions. In fact, they are the building blocks of convex functions via like supremums. So f of x here is equal to ax plus b. Okay, I don't need the vector notation. I'm just talking about R. So let me just write it as f of x is equal to ax plus b. Okay, so now this inner product u dot x is nothing but product of two things. So this yx minus ax minus b. So this is the function fx. Then y is supposed to represent that vector u. So here it's just a number, right? U dot x. So that is just yx. So I want to find the supremum. But this is again an affine function, right? So this is a linear function. If I just put y and a together, so y minus a times x minus b, and the supremum I have to take over x, all values of x. So now this is bounded if and only if the slope is 0, if y minus a is 0. Otherwise, a linear function will never be bounded. So this is bounded if and only if y is equal to a. So which means domain of f star is a singleton set A, and f star of A is equal to minus b. So because it's just a constant function minus b, when you plug in y equals a, then you get the constant function minus b, and the supremum is going to be minus b. So the domain is just a singleton set. Okay, let's look at a second example. It's a negative logarithm. This is again a convex function, but on a different sort of domain, on 0 infinity. So fx equals minus log x on r strictly bigger than 0. So that's a convex function. Now again, we want to look at xy or yx minus of this function, which is plus log x. Now this is unbounded above if y is bigger than equal to 0, because a linear function will always dominate logarithm eventually. Logarithm grows very, very slowly. In fact, the slope is 1 over x, which goes to 0 as, so the derivative is 1 over x, which is the slope, which goes to 0 as x goes to infinity. But derivative of xy will be y. Yeah, so it will be y. If y is strictly positive, then it will dominate log x. Actually, in this case, I don't even need that. Sorry. So both of them will be positive quantities, and log x is unbounded. So okay, so I don't need the domination of log x by linear function. It's just straight away. So this reaches maximum at x equals minus. Yeah. So domain of, let's say, f star is contained in r strictly less than 0. So here, when I say f star takes it's a function of y. All right. So when does this reach maximum? If y is negative, for that we just have to take the derivative and set it equal to 0. So derivative of xy plus log x. So with respect to x will be, so this, if I'm thinking of, so g of y, so gxy. So I want to find supremum of gxy with respect to x. Y is fixed. So then I take dg dx, or partial g partial x, which is equal to y plus 1 over x, which means if I set it to 0, I'll get x is equal to minus 1 over y. So reaches maximum at this point. So the value of f star at y is, in fact, I have to plug in this value, x equals minus 1 over y. So I get a minus 1 plus logarithm of minus 1 over y. So I'm putting in the particular value of x. And this is nothing but minus y is absolute value of y, because y is assumed to be negative. So this is minus y minus log of absolute value of y. So domain of f star is equal to, and f star of y is minus 1 minus log of y. All right, so this is the conjugate of the negative logarithm. Then let's look at exponential. F of x is equal to e to the x. Again, you'll have to look at this function xy minus f of x. So this is unbounded if y is less than 0, because my minus e to the x anyway is unbounded. So if y is less than 0, it is unbounded. For y bigger than 0, xy minus e to the x, if you take the derivative with respect to x, you end up with an equation y minus e to the x. So this means it reaches its maximum at x equals log y. So then you just have to put in this value x equals log y to find f star of y. So which means f star of y, you plug in x equals log y. So you have a y log y minus e to the log y is y. So domain of f star equals this. All right, so this was functions in R, some very familiar functions in R. Now let's look at some examples on Rn. So conjugates of convex functions on Rn. All right, so this is a very important example. So we had said that actually a lot of things about linear programming generalizes to convex optimization, and in fact one of the first problems you'll see, the next level problem, is quadratic optimization. You have a quadratic objective function, and you have some space, perhaps it is unconstrained, meaning it is all over Rn and you want to maximize that, and so on. So those are quadratic functions, assuming they are given by some positive definite form, they are going to be convex functions. And in fact, that is part of the one of the assignment exercises. And when you do least squares regression, for example, that is an example of unconstrained optimization where the parameters beta 0, beta 1 can vary all over R2, and you're trying to optimize some sort of quadratic function, which is convex. So I'm just trying to foreshadow certain applications. Okay, strictly convex quadratic functions. So f of x equals half. So this is q, and q is positive definite, meaning it is also invertible. All the eigenvalues are strictly positive. So for this, if we are trying to optimize this half x qx, now this is bounded above as a function. So this is bounded above as a function of x. For all y. And supremum over so it attains its maximum at x equals q inverse y. And if I plug that back in here, so x equals q inverse y, what I'll get is f star y is equal to half of y q inverse y, which is again a convex function because q inverse is also positive definite. So half of y q inverse y, and domain of f star is all of Rn. Okay, so this is actually something you may even have seen in analysis 3, trying to kind of optimize this sort of function when you're talking about like order 2 curves, like dimension 2 curves or something like that, or like conic sections. So you may have seen these type of expressions there. It is a matter of completing squares. So you have a term y dot x here, you have this half x dot qx. So you complete squares, and you may have to add a constant term in order to complete squares, but that just means that it is still bounded above. So it won't change where the maximum is attained. And if you do believe that x equals q inverse y is where this attains maximum, then it is easy to check that f star y is this, because you plug x equals q inverse y, and then here you'll have q inverse y dot y. So 1 minus half is a half. That's where you get this. So these two terms will actually be identical, barring this half term. But how do we check that it has attains its maximum at x? So if you remember the thing about conic sections and like trying to derive where these quadratic functions attain maximum, then perhaps you can immediately see this. Otherwise, it's just a matter of completing squares, as I said. So I want to translate this by some amount. says that this is precisely equal to y dot x. So I want to find a fixed alpha which does not depend on x, says that this happens. This is what we would call plus some constant. So the constant term will actually be alpha dot q alpha and a half. So anyway, that constant doesn't really matter. What we really want to figure out is what this alpha is. And in that case, it's just a matter of comparing terms. So the left-hand side looks like half x dot qx. Then you have minus alpha dot qx. So a plus alpha dot qx. That's because you have alpha dot qx here and x dot q alpha, but q is symmetric. It's positive definite. Usually positive definite already contains the assumption that q is symmetric. So you can move q to the other side. So in fact, minus alpha dot qx will be the same as x dot minus q alpha. So, and there is a minus half here. So half plus half is giving you 1 here. And then the remainder term is minus half alpha dot q alpha. But in any case, this is the constant we'll add at the end after we have figured out what alpha is. So just comparing terms, these two match up. So we want these two to match up. So what I should choose is like q alpha x should be equal to y dot x, and this should hold in a formal manner, or you could say for all y and all x. So which means q alpha must be equal to y, or alpha is equal to q inverse y. So now backtracking, essentially I can rewrite this expression as minus half x minus q inverse y and so on. And then we're talking about maximizing a function of this nature. I have something like z minus z dot qz. Yeah, so minus of this. So minus of this, I want to minimize this. Sorry, I want to minimize this function. So if I want to maximize this minus half whatever, I want to minimize this. And we know that this is always bigger than equal to 0 because q is positive definite. So the minimum is when z equals 0. The minimum is attained at z equals 0, which means x minus alpha is 0, which means x is equal to q inverse y. So, okay, so this is a quick proof running you through why the supremum of this function is attained at x equals q inverse y. All right, so here we have also computed the conjugate convex function. All right, so there's a couple more examples, but I guess you get the idea. So one thing to note is, first of all, f star is convex. We already saw that as a supremum of convex functions. Another thing to notice is the conjugate of a conjugate gives you back the convex function. That is kind of a standard property you would expect. If wherever I use uses the word duality, you always expect this kind of mantra that dual of dual is whatever is the primal. Dual of dual gives you back the original thing. So this also satisfies that condition. And then the third thing one notes is Fenchel's inequality. It's actually a trivial inequality. Just like Jensen's inequality is a trivial inequality. Like I had said, it almost is a tautology. Once you have the definition of convex function, then the Jensen's inequality is just that the fact that f is convex. But the key role played is by the description of convex functions using other sorts of tests, like whether the Hessian is positive semi-definite, or whether the gradient has some sort of monotonicity property, and so on. So those are the ones that are like usable in proving convexity, and then Jensen's inequality kind of falls out of it. So Fenchel's inequality is similar. It just says y inner product with x is always less than equal to fx plus f star x, f star y, sorry, for y and x in the appropriate domain. And that is because how is f of x defined? That is f star y defined. That is supremum of y dot x minus fx, supremum over x. So of course it is going to be bigger than for every single x. So this is actually directly following from the fact that f star of y equals supremum over x, which is bigger than equal to. Okay. So since we have seen some examples of f and f star, you can immediately check
If I plug in, for example, this particular f, and now I have a formula for f star, what does it prove? It shows that y dot x, for example, is always less than equal to half x qx plus half y q inverse y. So this inequality is always true for any positive definite function. Okay. And in fact, if you choose q equals the identity, what do you get? Like a root mean square inequality, half norm x squared plus half norm y squared is bigger than or equal to inner product of y and x. All right. Now we come to the economic interpretation of the conjugate. So here, let's say we have certain resources R, a vector of resources R1, R2, Rn. So these are the resources consumed. And in fact, you can, in our linear programming notation, it was more like B1, B2, Bn. So here I'm just writing it as R1, R2, Rn. And then we have this function S. So this is sales revenue derived from the product. So here's there is just one product. So as a function of resource consumed. And it is no longer linear, but it may be convex. Yeah. So total amount paid for resources is a vector, like maybe call that a vector P. So P1 R1. So for R1 you paid per unit you paid P1 and so on. So total amount paid is P1 R1 plus P2 R2 plus Pn Rn. So now what is the profit? Profit is SR minus P dot R. Okay, which is looking very familiar with the conjugate function, right? So SR is the sales revenue you get as a function of the resources consumed. And P dot R is the total amount you have paid for the resource. So this deficit is essentially measuring how much like the gross profit you have made. So what is the maximum possible profit? So M of P as a function of P, it is supremum over R of SR minus P dot R. So this as a function of resource prices. Okay. So essentially you're trying to compare like from where to buy your resources so that you maximize your profit. So there are different vendors that are selling you the same resources but at different prices. So maybe a bit more for R1 versus R2 and so on. And you want to figure out from which vendor should you purchase your resources. So it turns out MP is precisely going to be minus of S star minus P. So maximum profit is related to conjugate of gross sales. So maximum profit is related to the conjugate function. And by the way, the conjugate function we defined for convex functions, but the definition you can use for any function. These nice properties like f star is convex, f star star is f, and so on. This will hold for how should I say? This will hold for convex functions, but this description, the economic interpretation of the conjugate, this is actually for any function. If S is convex, then very nice. You'll have unique supremum. So unique points, especially if S is strictly convex. Okay, scratch that. Yeah, so in general, like the conjugate function will talk about relation between like maximum profit and the gross sales as a function of resources consumed. All right.
So we'll very briefly revisit conjugate functions when we talk about Lagrangian duality. So now the time has come to actually do some optimization. So I keep repeating this point, but after linear programming, so far all we have been doing is set up the groundwork. We have defined convex functions. We have seen all these different sorts of inequalities, and we defined norms. And because norms are supposed to measure sizes of vectors, and in a lot of real life applications, what you want to do is want to see whether some sort of solution is the best or is closest. That means the error terms are the smallest. And Jensen's inequality was useful in determining that the LP spaces like this LP norm, if I define for a vector x1, x2, xn as summation xi to the p 1 over p, we in fact showed that this was actually a norm. And so if I want to measure whether some vector is close to another, I can use this norm to determine that. So yeah, so we set up the context. Now we'll actually move into the optimization territory. So the first thing we'll talk about is unconstrained optimization. Unconstrained meaning you have an objective function. Recall, like even in the first class itself, we had said, what is optimization? You have an objective function on your decision space. So you have your decision variables. There are certain choices you want to make. The objective function is measuring how good your choices are. And you want to find the best possible choice amongst that. So unconstrained optimization means that the decision space D is equal to Rn. So everything is possible. There is no real constraints on this. And then you have this objective function from Rn to R. And the question is minimize this function. So this is unconstrained optimization. Now, if f naught is convex, if the objective function is convex, then it has a unique minimum value. It may not have a unique minimal solution. For example, if it is flat, then of course, and it is like parallel to the Rn here, it's a constant function, in fact. In that case, there are many minimal solutions, but the minimal value is the same. For convex function, that is the in a sense a very special property. It has a unique minimum value if one exists. For example, since this is unconstrained optimization, and if you have a linear function, then the minimal value may not exist. But if you're talking about, let's say, quadratic optimization, and we have something of this form, x dot qx, and x is in Rn, we do know that a minimum value exists. In fact, that is equal to 0. So if a minimum value exists, then it must be unique for convex functions. And especially a lot of the times, if f naught is, so if f naught belongs to C1 Rn, meaning it is differentiable once and all its derivatives are continuous, then essentially your strategy is then solve gradient of f is 0. In fact, this is the strategy we have already seen even starting from high school in 12th standard, that we want to find minimum or maximum of a function, a differentiable function defined on some interval. Then in the interior, you differentiate set it equal to 0, then find the x for where it is satisfying f derivative of fx is equal to 0, and then look at the endpoints. There will be maximum 2 of them in one dimension, and then you figure out which is the global minimum. So that is a standard strategy. So here also, so analysis 3, where you have studied all these techniques about local minimum, local maximum, and so on, the gradient of f must be 0. And that's also an optimization problem. So to get all candidates for minima, and then you may have to look at the Hessian to conclude whether it is minima or not. Perhaps it is a saddle point, then you will have to do some other checks. All right. So this is like mathematically the way to proceed, but how do you do it in practice? There is something known as the gradient descent method. So numeric, so we'll not spend too much time on this. I'll just like give you a brief insight into this. So in practice, how would you do it? Let's say you know that your function is convex. So gradient descent is essentially saying, like, in order to find global minimum, all I have to do is figure out in which direction the function is decreasing, and I keep moving in that direction. Ultimately, I'll hit the minimum. If I'm here, I'll keep going this way, I'll hit the minimum.
if my function is not convex and looks something like this, if I start here, I'll hit a local minimum, but after that, I'll just be at a stationary point. But if I started here, I will never reach here because the descent is always going the direction of the local minimum. So you're looking at level sets. So it is dividing the whole thing into certain disconnected regions. So each level set. And if you're starting at a point in each of the disconnected region, it will go to a minima in that region. It won't go to minima in some other region. So at least it gives you a recipe to numerically find the minima. And how does it work? It just looks at the first order Taylor expansion. So for small enough d, for small d, you have f of x plus d is nothing but f of x plus gradient of f x inner product with d, and then you have some second order terms which we're assuming to be small. So here, let's say you arbitrarily start with a point x, and then you are able to compute gradient of f. Like solving this is not an easy problem, right? Gradient of f equals 0. Solving that is not easy. Let's say you have some polynomial or something like that. Perhaps you can try different methods to do that. But in general, if I give you even a smooth function, figuring out when gradient of f is 0 is not an easy problem. So this gives you a numerical way. But it could be that computing gradient is actually easy. Solving this may not be easy. Gradient of f is easy. So if you give me a point x, I can compute f of x. I can compute gradient of f of x. And then what I do is I want to find the direction in which there is minimum in where it is decreasing. I want to go to minima, right? So where it is decreasing. And what was the interpretation of the gradient? So gradient of f at x is the direction of maximum increase. Of f. And why so? Look at this expression. So we want to maximize f of x plus d subject to d satisfying some norm condition, subject to, so maximize, or in our case actually minimize f of x plus grad f x d, norm d is equal to 1. In which direction should I move? Or norm d equals epsilon. I want to move a little, like a small enough direction, otherwise the Taylor approximation itself does not hold. So here this is the Euclidean norm. So I want to figure out a direction d such that this is minimized. So f of x is fixed. So I want to minimize this quantity, and that will hold if and only if d is minus, it's pointing in the negative direction of this. These are inner products. So this is nothing but norm of fx, norm of d, which is epsilon, cosine theta, where theta is the angle between them. These two are fixed numbers. The only thing I can really change is this theta. So if I make the angle between them minus to be minus pi, or rather pi, like 180 degrees, doesn't matter. So let's say pi. So in that case, this quantity will be minimized. So I have to choose d to be equal to epsilon times minus of grad fx divided by norm of grad of fx. So this is making it a unit vector, and epsilon is the norm of t. So in essence, so initialize, let's say, with some arbitrary vector x naught, then update. So x1 is equal to x naught minus epsilon grad fx divided by this. So the d that we have chosen here. So now from starting from x, we moved x plus d. So we know the value of f of x1 is in fact less than value of f of x naught. So we have decreased our value. So next what you do, you choose x2 to be equal to x1. Here I should also put x naught. So these are all x naught. Then minus epsilon grad f of x1 x1. So in general, so once you have the value of x1, you compute all these numbers, then you update to x2. So at the k plus 1th iteration, the way you'll define it is xk you already know. So then you can compute the gradient at xk. Then you compute this quantity. And eventually you hope that this will converge, at least in the local minima. It depends on the step size. If epsilon is too big, what might happen is, if epsilon is too big, So let's say bigger than this quantity, what might happen is you might jump over to this. Like you were coming down here, then your epsilon is so big and this turn is so light that you jumped over to the next local minima. So that can happen. But then you may jump to next minima. But by controlling the value of epsilon, you can ensure that this gradient descent method actually converges to a local minima. And then eventually grad f will be 0. So terminating condition will effectively be given by, this is like a Cauchy sequence. Is Cauchy sequence appropriate sense? In mathematics, saying something is Cauchy is very easy. All I just say for every epsilon, there is some n, so that after that, the difference xk minus xk plus 1 is less than that epsilon. But here, like how do I choose? How do I choose my terminating condition? So Cauchy just means that I will have this delta. I'll say that if xk minus xk plus 1 is less than delta, that is the moment I will terminate. What might happen is in the rest of the terms also that same delta might occur. Like just because xk minus xk plus 1 has norm less than delta does not mean xk minus xk plus 2 also will have norm less than delta. But then you choose delta very small, like for example, maybe like 0.0001, something like that. Then assume that that will terminate. So we'll get something close enough to the minima. All right. So in practice, when you're doing unconstrained optimization, then you really want to solve this grad f equals 0 to get all candidates for minima. But then you have this numerical method called gradient descent, which you can use to get like very close to the value of minima. And that in most practical problems, it might be good enough. You don't care about finding like the exact solution. Approximate is good enough. All right, so this was about unconstrained optimization. The next thing is constrained optimization, which is the one which is actually more familiar to us. In linear programming, in the simplex method and so on, we were talking about constrained optimization, where we had a linear objective function and we had a decision space, which was polyhedron. So similarly, here the problem will be you want to minimize a function. Note that I'm not saying f naught is a convex function. I'm just saying I want to minimize, perhaps it is smooth or it could be piecewise linear, whatever. I want to minimize this function subject to certain constraints. So I have certain constraint functions. Gix is less than equal to 0, I equals 1 to m, and hjx is equal to 0, j is equal to 1 through p. So for linear programming, remember all of these are just linear. The cost function is linear, this inequality constant is linear, this equality constant is linear. So just to emphasize, let me just say no need to assume f naught or d. So d meaning this set we're calling D, the decision space, are convex. And in fact, there are many problems, especially when f naught is smooth. Like I said, you just want to look at the gradient set it equal to 0. So there are many problems where you really don't want the convexity as. And in fact, there are many problems, especially when f naught is smooth. Like I said, you just want to look at the gradient set it equal to 0. So there are many problems where you really don't want the convexity assumption. But somehow, in general, you can get some sort of convexity out of this problem. So that's what we'll see in the rest of the lecture. Okay. First, we'll look at some special cases to try to understand this problem. Already, this might be looking familiar to you. Again, I will come back to analysis 3 because analysis 3 itself involves a lot of these problems, Lagrange multipliers. That may be something that is familiar to, where you are minimizing this function subject to these constraint functions where these gi's are also smooth, or c1 at least, hj's are also smooth. You have these constraints and you're trying to minimize this objective function, which is also nice and smooth. So that is kind of leading us to the theory of Lagrange multipliers, and that's what we'll do. And perhaps it will be a revisit for you. If not, then it is, like I said, it might be a foreshadowing. I remember, I think analysis 3 towards the end,
you do Lagrange multipliers. So you'll see it twice, so much the better. All right, so special case, I want to minimize f naught x or forget about the equality constants, subject to g of x is less than or equal to 0. So here one inequality constraint. So we'll try to understand this. And the way we'll do it is what is known as the method of Lagrange multipliers. All right. Now note that g of x equals 0 typically will define a n minus 1 dimensional surface. For example, g could be like, if you're in 2 dimensions, it could be x squared plus y squared equals 1, then it is a circle. Of course, you might have degenerate conditions like x squared plus y squared equals 0. Then it is a point. It's no longer, it is actually, if n equals 2, then it is no longer, that point is actually 0 dimensional. So forgetting about these kind of edge cases. So generally you expect that if I have this nice smooth function and I have just put up f of x is equal to 0, then this it is defining some sort of like an n minus 1 dimensional surface, and might look familiar when you read about implicit function theorem and so on. All right, so now let's look at this function. This function is known as the Lagrangian of this g. So Lx lambda is equal to f naught x minus lambda times gx. I will actually combine the objective function and the constant function via this new parameter lambda. So this is known as the Lagrange function related to this optimization problem, and this lambda is known as the Lagrange multiplier. We are multiplying with the constraint, or this is also known as the Lagrangian. Okay, this is an L, by the way, Lx lambda. All right, so I'm trying to optimize f naught here. Now let me split this decision space. So d equals g of x less than or equal to 0. I'm going to split this up as g of x is strictly less than 0 union g of x is equal to 0. So it has two parts, right? And this, generically speaking, will have non-empty interior. It will in fact be something which is n-dimensional, because g is a continuous function, g is assumed to be smooth and so on. So here maybe let me just say f naught g are C1. So these are all like differentiable ones and continuous. So since g is continuous, you know that this interval like minus infinity to open interval 0, the inverse of that is exactly this set, and that must be also an open subset of Rn. So here, once we are in this open set, we are trying to maximize f, right? So then the condition you have is grad f equals 0 for x naught belongs to, so x naught such that g of x naught is strictly less than 0. So this is one set of conditions. You want gradient of f is equal to 0 if we are the feasible, like interior of the feasible set. So then you have a few candidates by looking at this unconstrained kind of condition, gradient of f is 0. Now, if we focus on gx equals 0, that is actually the crux of the matter here. Now, g has some level sets. Gx equals -1 and so on. So let's say this is corresponding to -1, this is corresponding to 0, this is corresponding to +1. So these are contours of g or level sets of g. Level set meaning you're setting g equal to something and you're looking at all those n-1 dimensional surfaces satisfying that condition. Now, one thing is clear is that g does not vary on these level sets. That's the definition of a level set, right? So if I'm looking at the gradient of g, so remember, if there is some angle which is not 90 degrees, then that would mean that along this direction, there is some increase or decrease. Either there is some increase here or decrease here.
or increase here or increase here because the angle is not 90 degrees. But since it's a level set, the g is constant actually. So the derivative must be 0. So that means the gradient of g, so gradient of g is always perpendicular to the contours of g. Gradient of g is the direction of maximum increase. And in fact, if it is not perpendicular, then there is some kind of component of the gradient along this level set. But level set is where the function is constant. You can rigorously prove this by taking curves inside this level sets and looking at the chain rule. Like you look at g of gamma t equals c, then take the derivative with respect to time, you will get grad g, and this will be equal to 0 because c is a constant function in time. So from there also you can conclude rigorously, but here I'm trying to give you a geometric picture. So the gradient of g must be perpendicular to contours of g. Now what about f? Now f is defined on one of these level sets, gx equals 0. Now consider the values of f on the level set gx equals 0. Gx strictly less than 0 we have already taken care of. It is no, like the conditions have no dependence on g anymore. Once you know that it is in an open neighborhood, all you have to do is set grad f equals 0. That's all. But when gx is 0, there is some dependence that is going to come in. If so, what is grad f? Grad f is where the value of f is increasing. So let's say this is level set of g, and this is a point. So grad f is where the value is increasing. And if this is not normal to g, then there is some direction where the value of f will increase. So if x naught such that g x naught is 0 is a minimum solution or a minimal solution for f naught, then grad f naught is perpendicular to gx equals 0. Again, the same reasoning. If f is minimum here, it cannot increase along the direction of the level set because then it won't be the minimum anymore, right? So then it must be perpendicular to that. So we have this curve where grad g is also perpendicular and grad f is also perpendicular, which means this implies grad f naught is equal to lambda grad g for some lambda. And this is in fact the method of Lagrange multipliers, right? What you do is set this equation up. So this is at the x naught, at the minimum. That you set up grad f equals lambda times grad g. Then you solve for x naught and lambda, and then you check for feasibility. And x naught belongs to the feasible set. So this is a very nice geometric interpretation here. Then let's up the ante a little bit more. Let's say you have two surfaces. Here we are just talking about two, like just one constraint. So now let's talk about two constants. Okay, so if there are two constraints like g1 and g2, so these are some surfaces so that the intersection is like a line. So what you have is grad f must in fact at the point of minimum must be equal to lambda 1 grad g1 at x naught plus lambda 2 grad g2 x2. Sorry, x naught, same x naught. So here the problem is minimize f naught subject to g1 x naught is less than equal to 0, or since less than part we have taken care of, g1 x naught is equal to 0 and g2 x naught is equal to g1 x is 0 and g2 x is 0. So you want to minimize this function. By the same reasoning, the gradient of f must be in the span of gradient of g1 and gradient of g2, because if it is not, then there is a direction of increase in the intersection of these two curves. So it brings us to the general Lagrange multiplier theorem. So let me state the theorem without proof. And we'll do one small example to illustrate how the method works, how this optimization method works. So let f naught from Rn to R be the objective function. and G from Rn to Rc. So C is the number of constraints actually. So that's why I've written with a dimension. So there's C many constraints. Each component of the target is actually a constraint. So be the equality constraints. So both in C1 of Rn. Now let X star be an optimal solution. So let X star be an optimal solution to the following optimization problem. Be an optimal solution minimize f naught x subject to g of x is equal to the 0 vector. So essentially like this g1 and g2 right here, I have combined into a one single function g, and here in the previous example c was equal to 2. Such that this subject to this, so this is the optimization problem. This is the optimization problem. And such that rank of, so this is a technical condition we need, this is some sort of transversality condition. Rank of dgx star is in fact, it is like full rank. The rank of dgx star is equal to c. Here note that, for example, g1 and g2 could have been the same function. Then all this reasoning I'm using would have failed. Here I'm assuming some sort of transversal intersection, like some sort of intersection like this rather than they being the same function when I'm using my reasoning. So this condition is assuring us that. So let x star be an optimal solution to this such that the dg at that particular optimal solution is full rank. dg is full rank at that. Then there exists unique Lagrange multipliers lambda star in Rc. So each multiplier variable corresponds to the number of constraints. If there is one constant, there will be one Lagrange multiplier variable. And if there are n many constraints, there will be n many. There are c many here, so c many constraints here. Such that the gradient or the derivative of f at x star is in fact equal to lambda star transpose times dg x star, which is essentially a generalization of the statements here, right? This I could have written as lambda 1, lambda 2 times gradient g1, gradient g2, which will give us the total derivative of g if I write g equals g1, g2. So it's a general form of that. So how does the method of Lagrange multipliers work? So we'll illustrate that with a small example. So let's say our objective function is f of x naught equals 8x squared minus 2y, and subject to, so we're lying on a circle. So subject to this constant, x squared plus y squared equals 1. So what would the method of Lagrange multipliers say? That if I want to optimize it here, then I need gradient of f. What is gradient of f? So let's say at xy. So first of all, here I will have 16x. Here I will have a minus 2. So this must be in fact equal to some lambda. So there is one constant here. And the gradient of this function is 2x, 2y. So there must be something in this feasible set. So you need to satisfy this equation and x squared plus y squared equals 1. So we should never forget this. So this is a general condition, the Lagrange conditions, that whatever optimal solution you have must satisfy. But at the same time, the optimal solution must be feasible. That kind of goes without saying. So we always have to check this, x squared plus y squared equals 1. All right, so how do we proceed? We have equation 16x equals lambda 2x. And we have minus 2 is equal to 2y. So the first equation tells me that 2x times 8 minus lambda is 0, which implies either x is 0 or lambda equals 8. So I will take two cases. First case, x equals 0, then I look at my constraint. So if x is 0, y must be plus or minus 1. So this gives us two candidates for the minimum, 0, minus 1. So two candidates, I mean, both for minima and maxima, but let's say we just care about minimizing. Now case 2 is lambda equals 8. So note that here you had 2 lambda y. Actually, this is a lambda times 2y. So here I have assumed lambda equals 8, which means lambda times 2y. So 16y is minus 2. So y equals minus 1 over 8. Then again, I look at feasibility. So what the only options I have for x by solving x squared plus y squared equals 1 is plus or minus square root 63 over 64. So which is nothing but plus or minus 3 square root 7 divided by 8. So now from here also I get two candidates. One is minus 1 over, 3 square root 7 over 8 minus 1 over 8, or minus 3 square root 7 over 8 minus 1 over 8. So these are the two candidates I get. So 4 possible candidates. And these will contain all the maxima and the minima. Okay. And then you just evaluate the objective function, 8x squared minus 2y on all these 4 candidates, whichever will be the global minimum, that's it. So here I want to emphasize that no appeal to convexity has been made, because you must be wondering, right? Because we did so much about convex functions and we're trying to solve these optimization problems. But if you're thinking that convexity hasn't showed up, that's because it hasn't showed up, not because you're missing something. So no appeal to convexity has been made so far. Has been made. But something convex does start appearing, because this actually is a linear function, is an affine function of lambda. So in some sense, you're trying to solve certain linear equations, which are making your life simpler. I mean, linear equation in terms of lambda may not be in terms of x and y. So, and now we're going to make that connection actually. So here's a very important definition. Now, given the general optimization problem, minimize f naught x subject to these conditions, gi of x is less than equal to 0, I less than 1 less than equal to I less than equal to m, hjx is equal to 0, 1 less than equal to j less than equal to p. So we are going to define the general Lagrangian, not just with this sort of smooth functions or not. We will define a Lagrangian in general. So motivated by all these considerations. The Lagrangian associated with these optimization problems is, this is the definition. It's the function Lx lambda nu, which is f of x, f naught of x, this is the objective function, plus summation I equals 1 to m lambda I gi of x plus summation j equals 1 to p nu I hix. So this is the definition of the Lagrangian. And the condition that we had was essentially saying the gradient of Lagrangian is 0. The condition that you said, the gradient of f naught is a linear combination of this grad g and so on, is essentially telling you that gradient of Lagrangian is 0. So this is a reformulation of that fact. All right. So and yeah, so another part is that these variables are known as the Lagrange multipliers. The variables lambda 1 through lambda n, nu 1 through nu p, are called the Lagrange multipliers. All right. Before we move on to something more substantive, we need one more definition. So given a Lagrangian, so that means you already have an optimization problem in mind, and from that you have constructed this Lagrangian. So given this, did I put vector signs here? Yeah, I should put, so these are vectors, I must remind you. And this lambda 1, lambda m, so this is a vector in Rm, this is a vector in Rp. So m is essentially the number of inequality constants and p is the number of equality constants. So given a Lagrangian Lx lambda nu of some optimization problem, you can define something known as the dual. So over, let's say, domain D, the Lagrangian dual is the following function. It is defined in the following manner: f of lambda nu is equal to, you take infimum over the domain D of this function Lx lambda nu. So you fix lambda nu in Rn, Rm and Rp, or whatever are the appropriate spaces. Then over this domain D, you take the infimum of this. Or in other words, if I'm going to write out the definition of L, it is saying f of x summation I equals 1 to m lambda I gi x plus summation j equals 1 to p nu j hjx. Now note that as functions of lambda and nu, these are affine in lambda nu, and I'm taking infimum. And affine functions are also concave. They're actually both convex and concave, but here I'm going to use the fact that they're concave. Just like supremum of convex functions are convex, infimum of concave functions are concave. So that means no matter what optimization problem you start with, doesn't matter whether f naught is convex and so on. It could not even be smooth. But when you talk about this dual, this sort of dual problem, then this function is actually concave. So let me write out, since the dual function is the pointwise infimum of a family of affine functions, is the pointwise infimum of a family of affine functions, it is concave. It is a concave function. So where does convex optimization comes in? That we'll see once we understand the weak duality and the strong duality theorem in the context of these general optimization problems. So now we are going to make some connection with duality theory that we have already studied. Lower bound property. This is in fact borderline trivial the way it has been defined. Also known as the weak duality theorem. And in fact, we'll kind of see, in many examples that we'll see, we'll take linear programming. That's also an optimization problem. We'll see what the Lagrangian is. Then we'll see what the Lagrangian dual is. And it will turn out that it is precisely like the dual that we have already studied. So this is in fact a generalization of that concept and holds for any general optimization problem. Of course, I'm not trying to say that like in a sense that is just an immediate corollary. So this is the concept we should study. In that case, I would have started the course with talking about like convex optimization in its full generality. But historically, what happens is you recognize that, okay, these are the concepts that will generalize for convex functions, or
or in this setting, then you push it that way. So because we had recognized that duality was an important concept to study, in the case of linear programming, we sought duality for general optimization problems. So the historical causation happens always in the other way, not like someone decided, okay, this is a really abstract thing, that's what I'm going to study, and suddenly by magic, all the simpler things become easy. That's very like ahistorical, achronological, and typically a lot of math textbooks present things that way, but not very good for pedagogy, not very good for like appreciating what's going on here. All right, so weak duality theorem is immediate. So what does weak duality theorem say? That if we are trying to, like we had three motivations, remember, for duality. One of the things was to find an ad hoc lower bound. We had an optimization problem. Then we looked at some dual concept, and every solution to the dual concept gave you a lower bound. So that's exactly what's going to happen straight away from the definitions. Now, if lambda is bigger than equal to 0, if this is a constraint you give lambda, then f lambda nu is less than equal to p star, where p star is the optimal value of the primal optimization problem, of the original optimization problem, for which this is the corresponding dual. Remember, f we have defined here. F is the Lagrangian dual of some optimization problem. So if p star is the optimal value, did I write a vector? No, this is not a vector. This is optimal value. P star is the optimal value of the original optimization problem. And this you can clearly see. You just stare at this expression right here. What is GI? GI is, so for all feasible points, GI is less than equal to 0, right here. So if I multiply a positive number, the inequality is preserved. And Hj is equal to 0, so it doesn't matter what I multiply, inequality is preserved. So this quantity is always less than equal to 0, and this quantity is actually identically equal to 0. So when I do this infimum of fx plus this quantity right here is always going to be less than equal to fx. So hence, infimum of this quantity is going to be less than equal to infimum of just fx, which is precisely p star. That's the optimal value, right? That's the minimal value of f. So it's almost like a very straightforward statement from the way we have defined things. So proof, yeah, just a rehash of what I just described. So gix is less than equal to 0. So 1 less than equal to I less than equal to m. So lambda I gix is less than equal to 0. Since lambda I has been assumed to be bigger than equal to 0. And we know that hjx is 0. So 1 less than equal to j less than equal to p. Hence, for all x in the feasible set, fx plus summation I equals 1 to m lambda I gix plus summation j equals 1 to p nu I hjx is always going to be less than equal to f of x. All these are negative. So hence when I take infimum, it's going to be less. So f of lambda nu, by definition it was infimum, is going to be less than infimum of x over d of f of x, which is exactly equal to p star. And this should also look familiar to you. So initially, when we geometrically motivated duality using polar bodies, it came up as a very natural concept. But then we went through the more programmatic way of looking at it. We said, okay, we'll try to have some ad hoc bounds. So whenever we had these linear constraints, they were replaced by some variables which are always positive. Whenever we had equality constraints, they were replaced by variables which had no constraints. That's exactly what's going on here. These are ad hoc bounds. But the magic that happened in the case of linear programming is this ad hoc method actually gave you the optimal value. That was strong duality. So that will not be true here. But there are certain conditions on these functions f and g. For example, they assuming like f naught, g naught are convex and certain other technical assumptions, we can actually prove something known as strong duality. And those conditions are known as Slater's conditions. We will not see that in today's class.
But know that the strong duality does not hold here. But still, the ad hoc nature of our estimates that we had followed in linear programming, we are still doing here, which immediately gives us weak duality. All right, so now that we have formulated general optimization problems using this language, um, like our main goal essentially is a strong duality sort of theorem to kind of complete this whole analogy of arc between convex optimization and the special case of linear programming. Yeah, all right. So just quick point. So gives lower bounds for optimal solution. Just as in the case of linear programming. Now let's look at some examples so that you actually believe that these are non-trivial lower bounds. I mean, since it looks so weak, like since these conditions are just based on the fact that something is less than equal to 0 or not, so this might appear that this is really not doing much. So what really, how much good of a lower bound can this method give? Turns out it can give a lot of non-trivial lower bounds. And in fact, like I said, if Slater's conditions are satisfied, in fact, it will give you the optimal lower bound. But we'll get to that later. For now, so least L2 norm solution of linear equations. So we'll see some examples. Meaning, if you solve Ax equals B, it may have infinitely many solutions, right? Unless A is invertible, it may have infinitely many solutions. But amongst them, maybe you want the smallest. So minima is L2 norm of X subject to Ax is equal to B. So let's say this is a P by N matrix. So B is a vector in Rp. And X belongs to Rn. So essentially, just to rephrase what I just said, Ax equals B, you want to solve this. And of course, this equation shows up almost everywhere when you talk about applied mathematics. But then what you want is to find the smallest such solution, some sort of minimizer to this. Okay, so here let's compute all the Lagrangian, dual and everything. So what is the Lagrangian in this case? And by the way, minimizing this is the same as minimizing the square of it. And that looks a bit easier to handle, same as minimizing x dot x. This is just the square root of x dot x. But this is actually analytic in the sense it is differentiable and so on. It is smooth. So let us convert this into the problem of minimizing, in fact, norm x2 squared. All right. So now the Lagrangian is what? So here we have just equality constants. So there will be one vector nu, Lx nu is equal to the objective function, which is x dot x plus nu vec transpose Ax minus B. So this is the equality constant, Ax minus B equals 0. Now, so here note that the Lagrangian is a strictly convex function in terms of x. Because here this is nothing but x dot Ax, where A is the identity matrix, right? So for quadratic forms, so whenever you have a positive definite matrix here, then this is going to be a strictly convex function. And here the minimum is going to be attained at every x. So for every nu, so I mean minimum over x is going to be attained for every nu. For example, if you chose nu to be 0, then the minimum is attained for the vector x equals 0. And in the example we had seen just previously, so let me scroll back to it. Yeah, this is the one we had seen. We actually had explicitly computed the minimum, and the v, that is this mixed term, the y dot x term. So we already have seen this fact that the minimum will always be attained. All right, so the Lagrangian is a strictly convex function in terms of x, and it has a unique minimum because of the strict convexity. and in the previous case, we had actually found out that unique minimum. We had a formula for that. Okay. Now, so how do I find that? All I have to do is take the gradient with respect to x of Lx nu. So I end up with something like 2x plus A transpose nu, and I set it equal to 0. So the gradient is 0. This implies x must be equal to minus half A transpose nu vec. So for each value nu vec, I have this minimizer. So I'm just going to plug that back in to find the minimum value. So f of x nu, oh sorry, that's not the way I should do it. So just f of nu, right? F of nu was the infimum over x in the domain. So that means ax equals b of Lx nu, right? And we figured that at this point, the minimum is attained. So this is nothing but equal to L of minus half A transpose nu. There, this is, I just have to put in the value and I get. So this is my x. So x dot x will just give me minus half V transpose A transpose V minus B dot V. Okay. So here also I have put in the same value. All right. So now this is a concave function of V that you can immediately see because A transpose is positive semi-definite. So minus of that is going to be positive, negative semi-definite. So it's a concave function, which is something which we had anyway concluded by looking at it being a infimum of affine functions. But you can look at it directly also. So it's a concave function because as minus half A transpose is negative semi-definite. All right. So far we went through the motions. We figured out what the Lagrangian is. We figured out what the Lagrangian dual is, that is F. Then now we have to see what the lower bound property says here. So lower bound property, it says that if I plug in nu equals anything at all here, that is going to be less than equal to the optimal solution, right? So it's so it says minus 1 over 4 nu transpose A transpose nu minus B dot V is less than equal to P star for all V in RP, right? So essentially, like as you randomly put in all these V's, whatever number you get will in fact give you a lower bound for that. And what was the original problem? Original problem was to minimize this norm, like figure out how small can I make this norm. And this is already giving you an answer for that. All right. So now the second question maybe will feel more soothing because it takes us back to familiar territory, standard form linear programming. So what is the standard form? It says minimize C dot x subject to Ax equals b and x is bigger than equal to 0. And since here we are looking at inequalities the other way, so let's just say minus xi is less than equal to 0 for 1 less than equal to I less than equal to n. So I'm just rephrasing this in this form. Okay, so this right here is the standard form of linear programming problems. Yeah. So now again, I'll go through the motions. I'll define I'll just figure out what the Lagrangian is, then figure out what the dual function is, and then I'll figure out what the weak duality really says. So here, for the Lagrangian, here I have inequality conditions also. So I need both lambda and nu's. Here I just needed nu, but in this case I'll need both. So L of x lambda nu. First of all, I need the objective function f naught x, then plus this. I put a minus x because minus x is less than equal to 0. X is assumed to be bigger than equal to 0. Those are the sign constraints in linear programming. But here the notation I have used is I have either the equality constants or things less than equal to 0. So that's why I'm using minus x here. And in fact, that was necessary because in order to assume lambda is bigger than equal to 0, I needed the inequality to go a certain way. If you look at the proof of the lower bound property or the weak duality, so they have been all carefully phrased. It's not just a matter of sign, but it has been phrased so that the lower bound property is just immediately obvious. All right, so you have this, and then you have V transpose AX minus B. All right. This I can just combine together and write a C minus lambda. So what is the dual function? What is the Lagrangian dual? Which is f of lambda nu. Again, reminding you the definition. So x belongs to the domain, the decision space, which is precisely this. So there you're taking the infimum of this function L x lambda nu. All right. So this term, the v dot p term, doesn't really matter, right? Like in the sense that when I take infimum, because it's a fixed constant, it has no dependence on x, so I'll just remove it. And then I have, I'll put everything together. So plus infimum over this of the quantity C minus lambda plus A V transpose A dot x. All right. This is just collecting the x terms together. Actually, one has to be a bit careful. Okay, A transpose V. Otherwise, it will become a row vector. If you're thinking of C and lambdas as column vectors, so it should be A transpose V. Yeah, just collecting the terms of x together. So I have a C here, a minus lambda coming from here, and a v dot ax is nothing but ax dot v. Then I move the a to the other side. It's nothing but x dot a transpose v. Okay. So now that I have this, so what can be the infimum of this? Now this is a linear function, right? In terms of x, it is a linear function. So as a function of lambda and nu, yeah. So f of lambda nu is equal to minus infinity except when C minus lambda plus A transpose V is equal to 0. So why so? If this quantity is not equal to 0, then yeah, so as a function of lambda and nu, this is actually a linear function, right? So unless this is equal to 0, then it will actually blow up, like go all the way to infinity. Okay, so here x could be bounded, for example. Yeah, just a second. So when I define the Lagrangian, Mhm. Yeah. So finding this infimum, I mean, one should be able to use simplex method to do it. But yeah, I mean, the D may be a compact set, so this infimum will exist. Uh, I think I may have made a mistake in the definition somewhere. So let's see. I'm just wondering whether it should be D or all of Rn. Yeah, it has to be D, otherwise the weak duality will not hold. Okay, so in any case, let's forget about this. So at least this part is clear. F lambda nu is given by this infimum. So next, what I want to do is look at the lower bound property, what we derive from here. Now, if A transpose nu plus C is bigger than equal to 0, then so I have a minus lambda, and lambda is assumed to be okay. Let me okay. So if this is equal to 0, if A transpose nu plus C is equal to 0, then doesn't matter what x is, the infimum is 0. Then what we have is minus B dot V is less than equal to P star. Yeah, I think this makes sense. So we didn't really need this. I think there is some error in the book. So I'll have to check that. So yeah, so anyway, the dual function, it is clear that it is minus B dot V plus this infimum. And then the moment this is equal to 0, C minus lambda plus A transpose V is equal to 0. So lambda, I chose lambda is equal to 0, and A transpose V plus C equals 0. Right. So I just looked at F0 nu. So it's not V, sorry, it's nu. So I look at just F0 nu. So from that, I have B minus B dot V is something like this. So F0 nu is also going to be always less than P star, right? For any lambda nu, this is going to be true. I just choose lambda equals 0, and I choose nu such that A transpose nu plus C is equal to 0. Or in other words, you have this equation, this constraint A2 nu equals minus C. This might be actually beginning to look familiar. And we'll make it more concrete, but it's starting to look like the dual program. And minus B dot V was like some sort of cost function for the dual. B dot nu, I should say, again written as a V. And this is less than equal to the optimal value for P star. Yeah, in any case, so here the Lagrangian dual actually
like coincides with the actual dual. We'll see that shortly, but for now it is looking very suggestive. So let's look at one more example where we go through the motions of and see what lower bound the weak duality gives us. Yeah. So the third question, and part of the reasoning for looking at these examples is to say that although the optimization problems may appear in different ways, but the general principles can be used, or they can be reformulated in a way that makes it amenable to what we have discussed so far. For example, this one, two-way partitioning. So you want to minimize this function x dot wx subject to, you are used to conditions where the decision space is very nice, smooth, or at least continuous, but this will be a discrete space. So xi is equal to plus or minus 1. I equals 1 to n. So why would you care about such a thing? First of all, note that this is a non-convex problem. Your decision space is not convex or even nice. It's just 2 to the n points. Either x1 is plus or minus 1, x2 is plus or minus 1, and so on. So this is a non-convex problem. And feasible set, or the decision space, has 2 to the n discrete points. Here x is supposed to be in Rn. So that's why you have 2 to the n discrete points. And the interpretation of the problem is the following. You want to partition a set into two parts, and there is a cost associated with putting two things in a certain group or not putting them. Like maybe they're very good friends, and if you put them in the same group, then you get a benefit out of it in terms of work or whatever. So essentially the interpretation is you want to partition 1 to n in two groups, in two sets, and wij is the cost of assigning I and j to the same group, to the same set, and minus wij is the cost of assigning ij to different sets. So assigning them to different sets actually might be detrimental. So here you want to figure out a way to, you want to find the best way to figure out the partitioning so that this sort of scoring is minimized, so that the sum of these wij's, so anytime +1 and +1 is there, then you get a wij. Anytime there is a -1 and a -1, you get a wij. But anytime they have opposite signs, you get a minus. So clearly this is the way to formulate this problem. You want to minimize this sort of score, keeping track of what happens if you put them in the same group versus different groups. So here, what is the Lagrangian? So here we just have equality constraints. So we can just think of Lx nu. There is no lambda here. It is nothing but x dot wx plus summation I equals 1 to n nu I times xi squared minus 1. So these are the constants. Xi being plus or minus 1 just means x squared equals 1. So those are the constant functions, xi squared minus 1. So this is the Lagrangian. Now what about the dual? So that's f of nu. So you have to take the infimum over all of Rn. One to n nu I xi squared minus 1. Yeah, okay. This is something I'll clarify in next class. So I think you are pretending that there is an extension of your function, like your objective function also, to the whole of Rn, and the Lagrangian dual is being defined on all of Rn. And in some of the cases, I mean, all these properties that I mentioned, the weak duality, strong duality will hold. Yeah, so that is something that has, I'll check and confirm next class. So there is a little bit of confusion about the domain of where you're taking this infimum.
Like ideally, you should be thinking of taking it over the decision space or the feasible set, because as we saw in the proof of the weak duality, we are using those inequalities, and like gix is less than or equal to 0 and so on. So if you're taking infimum on a bigger set, actually that should be fine, right? If you're taking infimum of over a bigger set, then no worries. Like yeah, at least at those feasible points this equality holds. Okay, for the moment just bear with me and assume that I can take x to be in Rn. Okay. All right, so I can rewrite this. So nu I xi squared, I can rewrite is this as a like a definite form as x dot diag of nu x. So x is a vector x1, x2, xn. Then diag of nu is essentially a matrix which has diagonal entries nu1, nu2, nu-n. So I can rewrite this term, and then you have a summation I equals 1 to n nu I term. That's a different term right there. So this infimum I can think of as x w plus diag of nu. That's exactly what I've written. I've isolated this term dot x, and then you have a remainder term which is summation of nu I, which I'm going to rewrite as a in this form. So this is just a vector of ones. It consists all the way of ones. So when I take this 1 transpose v nu, sorry, that's nu1 plus nu2 up to nu-n. So now when I'm taking this infimum, this part is fixed, and this part will actually be 0 if w plus diag nu. So this is going to be 1 transpose nu if w plus diag nu is bigger than or equal to 0. If this is positive definite, for x equals 0, you will have this infimum. It will always be bigger than or equal to 0. So the infimum of this total term will be minus I transpose v, if this is positive. If it is not positive, then there is some direction where it is negative, right? So if you go in that direction very far away, so if you, let's say, diagonalize this matrix and look at one direction, the corresponding eigenbasis or corresponding eigenvector, which corresponds to the negative eigenvalue, then if you increase the value of x, then this will go all the way to minus infinity. So this infimum will be minus infinity otherwise. All right. Now what does that tell us? So now if you use the weak lower bound property, so we have computed the dual. So from the lower bound property, we have that P star is bigger than or equal to minus 1 transpose nu if W plus diag nu is bigger than or equal to 0. Clearly from this condition, if this condition holds, then this f of nu hat is this, but we know that for any possible value of nu hat, f of nu hat is always less than or equal to P star. If it is minus infinity, that's obvious. So that is, this part is not really giving us anything. So we're looking at this condition. But we do know that if I choose my vector nu to be the minimum eigenvalue of W, take a negative of that, times this. So I am repeating minus lambda mean W n many times. So gives the following lower bound. Lower bound. That P star, so minus 1 transpose this becomes n times lambda mean W, where lambda mean W is the smallest eigenvalue of W. Note that if I have minus lambda mean, it's clear that W plus diag of this thing, it will be subtracting the minimum eigenvalue from all of the eigenvalues. So it will all be positive eigenvalues. So this matrix will become positive semi-definite. So if I do that, this is the lower bound I get. So immediately, without even solving this problem, what you can say is the worst score, sorry, the best possible score is in fact bounded below by n times the minimum eigenvalue of this matrix W. That's the scoring matrix that you have, W. And of course, all of these are real numbers because W is assumed to be, so W, I guess, is a Yeah, it's a symmetric matrix. So if you exchange ij, it doesn't matter. The problem is interpreted the same way. Sending ij to the same set is same as sending ji to the same set. So W is a symmetric matrix and says all real eigenvalues. So this inequality is a non-trivial lower bound for the minimal score. Okay, so yeah, I mean it's almost 11. So I'll end with a last comment saying that, so when we look at weak duality, so this is always less than or equal to p star. That's what we concluded from the lower bound property, or the weak duality. So this is something also we got in an ad hoc manner from linear programming. But then we said, how about we maximize in terms of lambda and nu? Then we'll get the best possible lower bound from this strategy. So we want best possible lower bound from this strategy. And magically, in the linear programming case, the best possible lower bound turned out to be actually the best possible strategy. The maximum became equal to the minimum of the primal. But here, but at least we understand the formulation. So then it will become maximize f lambda nu subject to lambda bigger than or equal to 0. So we want lambda bigger than or equal to 0 so that this inequality is satisfied and we have this weak duality. So this finds best lower bound. And this is in fact called the dual problem. And since f is concave and hence it will be minimize minus f. So this is equivalent to minimizing minus f. Minimizing minus f, and minus f is convex. So naturally, when you're looking at the dual problem, that minimize minus f subject to lambda bigger than or equal to 0, that is actually a convex optimization problem. And we know that if you find the best possible lower bound, that is giving you a lower bound for your original problem, which may not have a convex decision space, it may not have a convex objective function, and so on. So this is the connection that we have made for a general optimization problem to convex optimization, which is something which we think we have a good handle over. All right, so we'll continue next class, and I will clarify the definition. One of the first things I'll do is clarify the definition of the function f. Is it taking infimum over just the decision space or the whole of R?